Hello physics students, it's Mr. Kennedy here. Hope everybody's doing great. This is actually going to be our last online lesson. So we're going to have a little lesson today on parallel circuits. We did series circuits last time, but this is going to be our last lesson for the school year. And then when you're done with all of your quizzes and everything with that, then you are done with this course. So let's jump into it. Last time what we did is we did series circuits, and series circuits are circuits that have one element, one right after the next. Parallel circuits are a little bit different because they're more independent. If we're to draw them, let's say we've got our little battery here. Here's our battery, and we go up and we'll have a little break here, and then a resistor here, a resistor here, and a resistor here. And first you can see that these little branches, they look like parallel lines, so this is in parallel in that way. But your home, for instance, is hooked up in parallel because what it allows you to do is not have everything on at once. With a series circuit, we needed to have everything turned on at the same time because you had to have current flow through all those things, but here you don't. When we talked about the light bulbs last time and the whole Christmas lights problem, in series circuits, if one element breaks, if one element goes out, the whole circuit goes out. But in parallel circuits, that's not the case. And the reason is, if I've got a battery right here, if I have a break right there, if that circuit part fails, current can still go to the other parts. They can still go down here, and you'll be all set. So again, your home is hooked up in parallel, and many things actually are, because it allows one element to be turned on with another element turned off, and you don't have to go through having everything on all at once. Now there are some drawbacks to this that we'll talk about in a few minutes, but the good part is everything is independent because everything has its own connection to the battery. So I'm going to remind you really quickly that we have our two coins that come in useful. V equals IR and P equals IV. So the voltage equals current times resistance, and power equals current times voltage. And those are going to help us just like they helped us with our series circuits. So let's take a look at this though. If I call this the total voltage of the battery, this is resistor 1, this is resistor 2, and this is resistor 3, these are going to add up a little bit differently than the last pieces did. But let's see what happens here. First of all, because every single one of these, resistor 1, resistor 2, and resistor 3, all have their own connection to the battery, that must mean they all have the same voltage. Because the voltage that comes here, the energy that this bottom part will get, is all the voltage of the battery. The energy that the middle part will get is all the voltage of the battery. And the energy the top part gets is all the voltage of the battery. Because you don't have to go through one to get to the next, they all get the total voltage of the battery. So the total voltage is equal to the voltage through resistor 1, which is the same as resistor 2, which is the same as resistor 3. All three of those get the same voltage. So there's your first step. Remember, in series circuits, they all get the same current. Here, they all get the same voltage. But now when you think about it, this is a lot like water flowing. So imagine you have the total current coming from the battery. It's coming out of the battery. It gets to here, and you can imagine this is like part of it going down one little tributary, part of it going down another one, part of it going down another one as the river splits off into forks and things. So that means I'll have a certain amount of current, I1, that goes to the top, a certain amount of current here, I2, that goes to the middle, and I3 that goes to the bottom. The current comes up here like water and then splits three different ways. But when it comes back together, it still has to be the same amount of current that I had before. So what this tells you is that the total current must be the sum of the three individual currents. And that's because the current can't go anywhere. It's not like it disappears part way. So the current comes through here, splits three different ways, comes back together, and now when it comes back together, it's whole again. And these two rules are opposite of what we saw with series circuits. With series circuits, current was the same everywhere and voltages add. With parallel circuits, voltages are the same and currents add. But now we can use this rule, or these two rules, to find out what the formula is for the sum of the resistors. And it definitely is a little bit different than what we saw with series. Because I have current, 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 and current right here, I'm going to cover up the current in my little coin up here. Current is V over R, voltage divided by resistance. So that means that the total current must be the total voltage divided by the total resistance. In resistor 1, we have current 1, that's voltage 1 over resistor 1, plus this is voltage 2 over resistor 2, because that's the current that goes to resistor 2, and then plus voltage 3 over resistor 3. Now if you notice, in all of those things, there's one thing that's the same. Now there's one thing that's going to cancel out. The voltage is the same in every single one of those resistors. So the voltage just drops out. And what you get here might be a little bit strange. You might be the first time you've ever seen this type of addition, but it's really this idea of reciprocal addition. That the total resistance, or better yet, 1 over the total resistance, is 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. So when you add them together, you're not adding the resistors, you're adding the reciprocals, and we'll see how that works here in just a minute. What this ends up meaning is that as you add resistors in parallel, the resistance goes down. Where when we added resistors in series, the resistance went up. But as you add resistors in parallel, the resistance goes down. Now, if resistance goes down, that means more current is going to have to flow. And the reason is you've got more space for it to go. Imagine you've got a hallway and you're trying to get through a hallway, and all of a sudden a new hallway opens up. If you have a new hallway that opens up, you can actually have more people flowing through that area. This is one of the drawbacks of parallel circuits, because if you keep adding things in parallel, then what happens is you can overload a circuit. For instance, imagine if you had a hair dryer on in the same room you were had in a microwave, and maybe have a toaster in that same room, and all of a sudden you trip the circuit breaker. The reason is you've gone over the amount of current that the circuit breaker can handle, and it has to trip. So every time you plug something new in, the resistance goes down and the current has to go up in a parallel circuit. So that's one of the reasons that you might actually trip a circuit breaker if you have too many things that are on inside of a parallel circuit. So let's take a look at one. I'm going to take a look at a relatively easy example, and we're going to go through all the pieces of it. We're going to find out what the total resistance is, what the total current is, what the voltage, current, and power through each part of the circuit are, and then you'll be ready to take a look at some practice problems. So here we go. And I'm going to make the numbers pretty straightforward because I just want you to get the feel for this right now. So we're going to take a similar battery that we did in our series idea, and I'm going to come up here, I'm going to break into one resistor, another resistor, and another resistor. And it doesn't have to be two, it can be, or it doesn't have to be three, it can be two, it can be four, it can be as many resistors as you want. But I'm going to call this a 6-volt battery, and then I'll say this top resistor is going to be 2 ohms. The middle resistor here is 3 ohms, and this one is 6 ohms. So, and we want to find out the following things. I'd like to find out what is the total resistance, what is the total current that's going to flow in the circuit, leaving the battery, and then what's the voltage, current, and power through each in each resistor. And I'm going to do a lot of this work right on the diagram because I think it's easier just to do it on the diagram. It keeps all the work together. The trickiest part is actually finding the total resistance because you have to do this reciprocal addition idea. So let's take a look at it here. If I want to find out the total resistance, what I do is 1 over the total is 1 over resistance 1 plus 1 over resistance 2 plus 1 over resistance 3. So let's see what we have. It's 1 over 2 ohms plus 1 over 3 ohms plus 1 over 6 ohms. Now, you could find a common denominator with this. You could do that. The problem is that I made the numbers really nice here, so it's going to work out. But if the numbers were not that nice, if this were 1 over 520 plus 1 over 330 plus 1 over 760, you're not going to find a common denominator. What I would rather that you do is just use your calculator. And what you do is this. I would say 1 over the total here is 2 to the negative 1. Put that in as your calculator, plus 3 to the negative 1, plus 6 to the negative 1. Put it in as inverse of 2, inverse of 3, inverse of 6. And then when you're done, what you'll do is you'll take the inverse of the whole thing, the inverse of that answer. So when you do it that way, what you'll come up with, and if we look at the inverse of 2, the inverse of 2 is 0.5. The inverse of 3 is 0.3333 repeating. The inverse of 6 is 0.1666 repeating. And if I add them together, what you'll see is I get 0.5 plus 0.33333 plus 0.16, etc. And I basically get 1. So 1 over the total here is 1. Now, don't forget at the end, to find the actual total resistance, it's the inverse of 1. And the inverse of 1 is just 1. So that's 1 ohm. The total resistance here is 1 ohm. Now, keep in mind, you could still do the common denominator. You can still do anything else you'd like. But I think this is a little bit easier when you do calculation stuff. Take the inverse of 2, take the inverse of 3, take the inverse of 6, add them all together, and then take the inverse of that number, and then you have it. The problem is most people forget to do the inverse of the last number. How do you know you're right? One good indication that you're right, the total resistance should be less than any of these three. If you find out that it's bigger, then you probably forgot to do the negative 1 part or made a miscalculation somewhere along the way. So what we know here, we know the total resistance is 1. It's 1 ohm. Well, now we can go back and find out everything else. We can use our little circle here. Voltage, current, resistance. If I have the total voltage is 6 and I know the resistance is 1, then I can find out the total current, because the total current then will be 6 volts divided by 1 ohm, which is 6 amps. Okay, so I've got the total resistance, I've got the total current. Now I'm going to find out the current and voltage through each. Some of this is going to be very, very easy, especially in this one because I've got my numbers so nice. But I'll know right away that 6 amps leaves the battery. 6 amps leaves the battery. It's going to go up here and split 3 different ways. But I already know something. The thing I already know is I already know what the voltage is through each one. Because the battery has a voltage of 6 volts, and each one of these has its own independent connection to the battery. This has 6 volts, this has 6 volts, and this has 6 volts. Now to find out the current through each one, what I can do is I is V over R. So 6 volts divided by 2 ohms, I'll use that in another color, is going to be 3 amps. 6 volts divided by 3 ohms is 2 amps. 6 volts divided by 6 ohms is 1 amp. So this makes sense. The one with the least resistance has the most current. That allows more current to flow. The one with the most resistance has the least current. And how do we know we did this correctly? 1 amp plus 2 amps plus 3 amps equals 6 amps. That these split into 3 going through the top, 2 going through the middle, 1 going through the bottom, and then recombine to be 6 later, and now you have a total of 6. But what about the power? And remember, power would relate to which one burns the brightest here. So let's go back to our power calculation, and we'll see what we get there. With power, get rid of this part for now. With the power, we know that power is current times voltage. Well, we have for each one of these, we have the voltage and current through each one. So current times voltage, 3 times 6, that's 18 watts of power. 2 times 6, that's 12 watts of power. 1 times 6, that is 6 watts of power. And notice again, the top bulb, the lowest resistance would burn the brightest. Now in series, it was the higher resistor that would burn the brightest. But here, if this were a light bulb, this would have the most power. It would have the brightest. Look at this, however. If I figure out the total power, 6 amps times 6 volts, that's 36 watts. 6 times 6, well look, 18 plus 12 plus 6 is 36. It all works out and everything came together then. So now you should try some of the problems with parallel circuits, and then you'll have one last quiz on this, and then we're done with physics for the year. So yeah, this was your last video. If you have questions or any problems or anything, please feel free to let me know. Please feel free to email me, or you can text me through Remind or whatever else you need. I want to make sure that you do great on these last couple quizzes. All right, everybody. Hope you're having a great day.